All right, so welcome back. Today in this video, we're going to be doing some more statics civil FE exam review. We're going to be focusing on areas and moment of inertia. So this is kind of like an addition to centroids because you're going to take some of the things that you learned from getting the centroid of an area to now inputting that into moment of inertia. So you're going to get some different shapes, and we're going to be going through some practice problems that will hopefully make sure that you're clear on these different concepts. So let's go ahead and dive right in. Number 1 says, find the moment of inertia about the x-axis for a T-shaped section shown below. Dimensions. Height of stem is 4 meters. Length of stem is 6 meters. And then the height of top part is 2 meters. And the length of top part is 8 meters. So looks like it's been drawn out for us below as well, which is nice. And so let's start by determining what we're given. So we're given this T shape. Okay. And we're given all the dimensions. All right. And we're trying to find the moment of inertia about the x-axis of this particular shape. So what this means is we want to take this shape, and this shape should have a centroid. Maybe it's there, right? And we want to find the moment of inertia about that axis. Okay, so where do we start? Well, first and foremost, we probably need to determine what the centroid of this shape is, right? Because I don't know, we can't guess that. It's a random shape. You can't just say the center of or the x-axis, the y coordinate of this is, you can't guess that. So we actually have to solve for that. So let's start there. Yeah, let's start there. All right, so how do we get that? Oh, we have to break it up into digestible pieces. So I'll say that this is my part 1. This here. Right. And then my other part is part 2. And that'll be this piece. And I'm being extra today, just so you get the difference. Okay, so what formula will we need to use to get the center of this piece? And not only the center, we won't need the x coordinate of this, we just need the y coordinate of this. Okay, so, and the reason why, I'll go ahead and go through the reasoning why. When you're finding moment of inertia, the main piece is dependent on the axis that you're going around. So basically what we're trying to do is we're trying to find the center of, or the centroid of the entire piece, which I think is roughly there. But we have to compare that to the center of each individual piece, which might be here and here. Well, not as far as y is concerned, right? It's going to all be in the Actually, I won't even confuse you like that. So I would assume that my centroid is going to be there of that piece and about here of this piece. All right, and there's some distances. There's some distances from these centroids, right? We're trying to find the moment of inertia about those. So it's called the parallel axis theorem. And we're going to need to know the distances so that we can, this axis is parallel to the centroids of these other pieces. So that's why we're trying to find the initial centroid, right? Which we can do now. So let's find y bar. So y bar is going to equal, how would we get that? Well, I'm going to search centroid. That's what it is. I feel like I've gone too far. Yes, so y bar is going to be here. No, it's going to be here. So it's your y bar of the entire shape is the sum of the y centroid of the individual piece times the area of that piece all over the sum of the area. So what I mean by that is it is the sum of the y times a over the sum of, and this you're going to break this up into pieces. So for part one, what would be our y centroid, the centroid of the piece in the y direction. So if this height right here is 4, right? What is the center? If I'm saying my axis just starts from the bottom, how do I get the center in the y direction? So I'm just going to say 4 divided by 2, or 2. All right. So the center of that piece is going to be at 2. Okay. How do I get the area of part 1? We're going to say 4 times 6, right? It's the area of this rectangular box. All right. Now it's time for part 2. So if I add I'm starting from my axis, which is here. Then where is my y2? So I'm coming up 4, right? But then I'm doing another 2. So how do I get to this center point? That distance. What is that distance? Well, it's 4 plus 2 divided by 2, which is 1. So it's going to be 4 plus 1, or 5. Right? Okay. So we got 5. So what's our area of the piece? That'll be 8 times 2. All right. All over the sum of the areas. All right. So what's the area of piece 1? Well, it's going to be 4 times 6 again. And then what's the area of piece 2? It's going to be 8 times 2. All right. And once you go through that process, you should get your y bar to be 3.2. All right, so what does that mean? That means the center of the centroid of this piece, the y coordinate of our centroid of this entire piece is at 3.2 meters from our reference axis. So that means that we're coming up and we're not going all the way up to 4, right? Coming at 3.2. Which I would say this is probably, let's call this 3.2. All right. What's the value? It's the centroid of our entire piece. Okay. So now that we have the centroid of our entire piece, how do we take that information and use it to help us get our moment of inertia? Well, we're going to use something called the parallel axis theorem. I don't want to confuse you. I'm going to erase some of these lines that have been drawn. So for simplicity purposes, the distance from here to the bottom is 3.2. And that's the centroid of the entire piece. Okay. So, all right. The next step is going to be for us to get moment of inertia. So when we're looking for moment of inertia, there's something called the parallel axis theorem. All right. Hopefully you can find it, be able to read it. But it basically just states that the moment of inertia of an area about any axis is defined as the moment of inertia of the area about a parallel centroid axis plus a term equal to the area multiplied by the square of the perpendicular distance from the centroidal axis to the axis in question. So what does all that mean? Well, you have two different axes that you're comparing things to, right? We have been, our reference axis is one axis, right? So that's this axis. It's this axis and this axis. Now, that's how we were able to get our centroid of the y coordinate. And we're wanting to find the moment of inertia about the x-axis of this particular piece. So we need let's try this again. So we have our reference axis, and then we have our centroidal axis, which is this orange line, right, that I've been kind of drawing over and over and over. Okay, now these two axes are parallel to each other. And it's kind of like here, right? That's the center. Here's our center. And so we just want to go ahead, find the inertia of the x, right? About the x-axis. So to do this, we need to say inertia in the x is equal to I xc plus dy squared times a. Okay. So dx or dy is the distance between the two axes in question. So what are the two axes in question? Well, we have the centroid. We have the centroid of the actual shape, and then we also have the centroid of the individual shape. Which could be like here. So that's going to be your dy. And then you also have the centroid of your other shape, which could be like here. So there's going to be a distance between the centroids of your individual pieces and the centroid of your whole combined piece. So you got a few different reference points that we're looking at. So let's start with the first piece of this equation, which is Ixc. So how do we get Ixc, or the moment of inertia of a specific area, right? Okay, so we break this up into parts again. So we would say, what's the inertia of part 1? So I just say Ix of 1. And that equals, well, what's the inertia of a rectangle? Okay, so here we have it. Ixc. So it's base times height cubed over 12. So it's going to be, what's our base of the shape? 6 times 4 to the third, right? Divided by 12. Okay. That takes care of this first piece, right? What's our dy? Well, it's the distance between the two reference points. So the centroid of the actual part 1 is going to be 2, right? In the y direction. It's half of 4. And then what's the distance of the centroid of the entire shape? So it's going to be minus 3.2. All right. And so you're going to square that. All right. And then you're going to multiply it by the area, which is, again, 6 times 4. Okay. So that's the moment of inertia of the first shape What's the moment of inertia, or what's the answer to that? So I get 66.56 meters to the fourth. Okay. What about our second shape? Ix2. That's going to be equal to 8 times 2 to the third. So this is base times height cubed divided by 12. All right. All right. What is our distance? What's the distance of the centroid, the y coordinate for the centroid of the second piece? So it's going to be your 4 plus 2 divided by 2, which is 5. 5 minus your 3.2. Right. So anytime you're looking at I'm trying to make sure that this dy is, it makes sense. Because I feel like dy is the most confusing piece of it once you understand. Parallel. Okay, so the parallel axis theorem. All right, so that dy is the distance from your reference axis to the center of the piece that you're looking at. So in this case, our dy, they give a pretty good explanation of it too. It's the distance between the two axes in question. So each of your individual pieces have their own centroids, right? Maybe orange isn't a good color because that's the centroid of the piece versus the centroid of the composite shape or the total shape. So each of those have their own centroid. So you just want to find the distance between the centroid of your individual pieces versus the centroid of the entire shape. And once you're able to do that, that is your dy. That's the distances between the two axes in question. Okay. All right. So once you total all that up for the moment of inertia and for the second piece, you're going to get 57.17 meters to the fourth. All right, but you're not done yet, right? Your total inertia about the x-axis of the shape is going to equal your 66.56 meters to the fourth plus your 57.17 meters to the fourth. That's going to give you your answer, which is 123.73 meters to the fourth. All right. So that looks like that's A. So main big things to understand is first, what axis are you looking to take your moment of inertia about? In this case, it was the x-axis for this particular shape. So we knew we were going to be using the x-axis, figuring out that. Another thing that we needed to pay attention to is this is not just a regular rectangle shape where this wouldn't be nearly as complicated, right? But since we had a composite shape, then we needed to find the centroid of the entire shape. So that is what made this a lot more complicated than it needed to be. Now, other things to mention is notice that if you're looking at your x-axis, or if it's about an x-axis, then y bar is typically important. Now, if you're looking at your y-axis, if you're trying to figure out the moment of inertia about the y-axis, then your x bar is what you need to be trying to find. So it would be in reverse, right? You would be looking for the distance between the two axes, and those axes would be dx, the change in x, right? From here to here. But what we were doing was we were going from reference axis to here, dy. So just something to keep in mind. Hopefully this made sense. We'll do some more practice just to make sure. All right. So number 2 says, how does changing the mass of an object affect its moment of inertia? All right. I'm going to do a search. They don't really give us too much. So they give us that we're changing the mass of an object, and we're trying to find how that affects inertia. Okay, so I'm going to do search for mass moment of inertia, maybe. All right, so let's look at what section we're in. Dynamics. So I don't. This is not really open. Okay. Definitions for mass moment of inertia. Mass moment of inertia about any specified axis. So looks like this formula could help us in terms of mass of the body. And so let's go through our questions and see if we can figure out, all right, if everything else stays constant, we change our mass, what happens? So increasing the mass, it decreases the mass moment of inertia. Well, if I keep everything the same, right, and I increase, so we'll say I nu is equal to IC plus MD squared. So if this is 1 plus we'll say my mass is 1 and my what's that, D, the normal distance from the bodies mass is 1 as well. And we'll say that's squared. All right. All right. So this is our initial conditions to get I new. So if I increase the mass, so if I say 1 plus 2 times 1 squared, what happens to my new moment of inertia? Well, it's going to be, this is equal to 2, and my new moment of inertia increases or goes to 3. So if I increase the mass, it doesn't decrease the moment of inertia. I know that that's not right. Increasing mass has no effect on the moment of inertia. I would disagree. Increasing mass increases moment of inertia. I would agree with that one. So, and increasing mass may increase or decrease mass moment of inertia depending on other factors. No. So your answer is C. And with any conceptual questions, you can always do that. Like you can always keep everything else the same and then plug simple numbers in just to see what happens in the equation. So don't let conceptual things scare you. Just think, okay, if I actually increase this, what happens to my final value, right? You don't have to worry about units and all that stuff. Just plug a higher number, lower number into the equation and see what happens to it. All right. Let's look at number 3. This one says determine the mass or determine the moment of inertia of a triangle about the x-axis. The triangle has a base of 8 and a height of 6. Okay. So we are given the moment of inertia. Or we're not given the moment of inertia, I'm sorry. We're given that is a triangle. We're also given that is supposed to be about the x-axis that we're taking the moment of inertia about. And given the base and height. All right, we want to find inertia. All right, so how do we go about this? So first thing I'm thinking is we need to go back to that chart that has, so anytime I want to find inertia, centroids, all that, I normally go to the chart with all the shapes that are in 2D if that's what I'm doing. And right now, that's what it's asking. So this chart, all right. Okay. So I'm going to say that we're looking about the x-axis, moment of inertia. So we're going to be using this equation. We want to find it about the x-axis of the shape. So we know that our base, so I xc is going to equal base times height cubed divided by 36. Okay. Our base is 8, so it's equal to 8 times 6 to the third. Okay, and then that gives me 48 meters to the fourth for my moment of inertia. So this wasn't too bad. I just had to figure out what you just have to know what you're solving for. So if this would have said determine the moment of inertia of a triangle about the y-axis, then we would have used this equation instead, right? But since it was about the x-axis, that's why we chose to talk. These refer to you taking it literally on along this axis instead of the centroid of the actual piece. So when they write this out on the test, they need to clarify. They will need to clarify, but typically it's assumed that it's about like determine the moment of inertia of a triangle about the x-axis. Asking it in that way, I assumed that we were using this triangle and taking the centroid about the centroid's x-axis. But if they say determine the moment of inertia of a triangle about, if they say they will need to denote clearly where they're saying. So they may even point it out and say, we don't want you to take the moment of inertia, because normally what you're doing is you're taking it about this axis, right? That's typical. But in the event that they say take it about this axis, they will make that very clear, because that can be confusing. But from what I've seen, for the most part, yeah, they want you to take it about the centroid's x-axis. So typically we don't use these unless they clearly denote and draw the axis that they're wanting you to use. So just food for thought. Okay. In the next section, we're going to be looking at static friction, and I believe that will wrap up the statics review. But let me check just to make sure. And as always, if any of this did not make sense, please don't hesitate to reach out. Yeah, so we did. So we've gone through centroids of area. So we've also gone through area moments of inertia on this one. So we'll look at static friction as the last topic for statics.